All right, here's an example for class 22. This would be example 4, where we have this sphere connected by a rod to a disc. It's going to connect with a spring. And is it released from rest or is it stretched? Let me see. The disc is pinned at O and it weighs 15 pounds and it's welded onto there. If the spring is originally stretched to 1 foot and the sphere is released from the position shown, determine the angular velocity of the disc when it has rotated 90 degrees downwards. By the way, we don't actually know, you have to be careful in this kind of setup. We don't actually know that it would make it all the way to 90 degrees downwards. The thing could balance out, right? But it's already got, and the spring already has some stretch in it. So we have to be careful sometimes when dealing with a problem like this, at least as a professor, that you don't set it up and make it all screwy. So I already set up a table as part of this so that you could find what the center of mass is going to be, and you could also find what the mass moment of inertia of the piece is. And so you could actually do this in parts instead of doing this this way right here, but I haven't shown it that way, so we'll just work through the way that I have it here. So I start off with the disc, right? That's disc A. Let's see, look back over here. So that's disc A, 15 pounds, 2 feet radius. This guy's 2 pounds. That's what that hashtag means, our pounds. 1 foot long, and then 10 pounds. And this is a sphere, which we don't usually deal with very often. So we'll look at that. So we get the disc right there, get the mass, and the distance from, let's say from the pin, right, is the distance we're going to use. So it has 0 because it's right there at the center. And then the sphere, we have it's 3.5 feet away from that. So that's what its mass times the distance is going to be. And the rod, that's in between the two of them. So we have these, and the total weight's 27 pounds, by the way. The total mass, though, is going to be 0.8385 slugs. We're adding up this column. We add up this column right here, so we have the really the first moment of mass, if you will, and that's 1.242. And so if we divide that 1.242 by the mass, we get, this is the location where the center of mass is of that piece, right? So it was like 1.4, so it's like right around in that location, right? So, and then we want to get the mass moment of inertia, so we get that of the disc, and we don't need to move that. We want to find the mass moment of inertia about the center, not about the center of mass, but about the pivot point. So that's not gonna change at all right here. But we take it of the sphere. Now that we look that up, that's 2/5 mr squared for the mass moment of inertia of a sphere. And so we end up with that value, but we do need to shift that 3.5 feet from its center of mass to be around 0.0. And then we do the same thing for the rod. That's 1/12 ml squared, and it has a pretty small mass moment of inertia on its own, but that once you add it to the mass times the distance that you have to move it, it gains a little bit, it makes it substantial. So we add all those together, and we can add them because they've all been moved to the same spot. And so we get a total IO, the mass moment of inertia about O right there, of 5.160 slug feet squared. So here's state 1 and here's state 2. We presume it's going to make it all the way there. I gotta actually, to tell you the truth, I don't think I came up with this problem, but I gotta kind of wonder if it's ever gonna make it to there, right? That's just my feeling, is that it might get hung up somewhere, because it would need some kind of motivation to get past a certain equilibrium point. But let's continue with this problem and not worry about it too much. And we needed this, by the way, we needed this distance right here, which appears to me to be incorrect. Okay, 1.481. that should be, oh no, it's right here. Okay, yep, yeah, 1.481 is the distance from the datum. We create a datum that's going to be at this center of mass's lowest point. By the way, we could have done this for each of the pieces. We didn't have to do this. We would have ended up with the same result. So there's no external forces, so it's a conservation of energy problem. So we start out at state 1 with no motion. We start out with state 1 with the potential energy and some spring potential energy right here. So we get there's like 41.99. And then with state 2, its kinetic energy is going to be moving, right? And we also note, I guess I jumped the gun and wrote what the stretch of this thing was going to be. So it's going to be an additional amount of stretch, right? So it starts right here and it moves down. So we got to figure, and it's going to move down an arc of 90 degrees. So that's the amount of stretch that this thing is going to add to it. So it has an initial stretch of 1, but then it's going to stretch an additional 3.142 feet. And so it's going to have this amount of potential energy right here. So it starts off here and it ends up here. And so we could figure out what the kinetic energy is going to be, because that's 1/2 I O omega squared. And so this is what we determine it to be. But the truth is that I'm not 100% sure it's going to make it all the way down there. It might because of momentum, but there might be a point where the forces balance out. I do believe that it would have a faster speed somewhere up higher, that it's going to start slowing down because of the amount of stretch of that spring. That's my feeling there. We could go ahead and try to think up like various scenarios where that would happen. But I don't know. This would be an interesting thing. I'd have to think about it some more, of different things that we might want to try to find. But most of the time, what we would need to do is find out where the potential energy was a minimum, would be where the kinetic energy was a maximum, right? So we have this balance of potential energies between this initial potential energy and this one right here. So I think if you could set these two equal to each other is, I wonder. That's where the speed's going to equal 0. Yeah, the speed will be 0 when those potential energy equals that potential energy. So, it's an interesting dilemma right here where we could. Anyway, we'll talk about it some more some other time. So that's all the examples for this section. All right, today's guitar is yet another black Gibson. Now, this was an impulse buy. This is another cheapo type of Gibson on the lower end. Now, these are considered melody makers, all right? But this is an SG shape. SG stands for solid guitar. Not really brilliant name. The SG shape really came out in like 1961. And they had Les Paul came out in, I think, in 1954, I think is the first model, maybe 1953, and went through a couple different changes, but then they decided to radically change it in 1961, and they changed the Les Paul to this shape. So there was a few years, I think maybe 2, where Les Pauls were actually this shape, and it would say a Les Paul on the headstock. But then people didn't like them. So they went back to the regular Les Paul shape, but then people started playing these things again, and so they came up with it. Angus Young of AC/DC plays an SG shape guitar, an SG. But this is actually a melody maker that they came out with a couple years ago, and Tim Britt, one of the guys in audio at CETA, he came by with his guitar one day, and he says, "Hey, check this out," and he just left it in my office, and I was like, this is kind of cool. It's kind of like my type of guitar. It's very stripped down. And I said, "Hey, are you selling this?" And he said, "Nah, I don't know." Anyway, I bought it off of him. I actually happened to have the amount that he wanted in my pocket. from playing a few gigs. And I honestly, tell you the truth, I don't like it all that much. But it's kind of a cool guitar because it's got that like minimalist thing. It's only got one knob. Even the wraparound tailpiece doesn't even bother to try to intonate the strings. There's one humbucker. I do like the headstock on these. They're a little bit straighter, and that can help for some amount of tuning instability. But it doesn't have a lot of like natural resonance as far as I can tell. You see, it doesn't make the wood vibrate. So the notes don't really like resonate into the body, I don't think, a lot. So it has kind of a sterile kind of sound to it. And I put in a different humbucker into it, but it should be a lot more powerful than this. It's a decent guitar.